Just a couple of administrative announcements before we get going. So as I'm sure you guys all know very well, the homework is due tomorrow. So hopefully you guys are well on your way with that. The midterm will actually be a week from today. I'll also, just maybe as a reminder, there'll be no lecture that particular day. I'll probably hold some extra office hours or something like that instead. But it'll be starting right, at that evening, so right at 6:30 p.m. sharp. That's no Berkeley time, no 10-minute delay, no anything like that. It'll start right then because I want to give you guys the full hour and a half to work on it. So keep that in mind. I've sent the request in for the room. I don't exactly know what that'll be yet, but I'll post an announcement on Piazza or on the website as soon as we figure that out. So be on the lookout for that. Just related to that, as I mentioned last time, I will hold a quote-unquote review session, which really just means I'll come in and answer any questions that you guys have. So please do come by for that. And for that one, actually, I don't know why I put Monday here. I was actually thinking of doing this Tuesday at 6 p.m. No, if I get the right color. Yeah, so I was thinking of doing this Tuesday at 6 p.m., probably just either in this room or over in 550 Corey. So anybody who cannot make that time or strongly prefers a different time? Okay, I may sort of re-poll the class when people come back in, but since you guys are the early birds and actually here, I guess you get the strongest weighting. So unless anybody has a strong objection to it, we will indeed hold that review session Tuesday at 6 p.m. of next week. And again, I'll post that on Piazza just so everybody sort of knows when and where to show up. All right, so any questions either on homework or material so far before we dive back in? All right, so last time we were basically finally getting into really looking at fully differential circuits, where again the whole point of really doing fully differential circuits was that by doing that we can actually now gain some immunity to common mode variations. Okay? We talked a lot about now, despite that fact, you do still have to be careful about the common mode, because if just from a DC standpoint it's sitting somewhere that's bad for biasing the amplifier, clearly things won't work. But nonetheless, the whole reason of really going fully differential is indeed to buy yourself immunity from common mode errors. And we'll come back to that in 1 second. Now, one thing that gets a little bit more, let's say, interesting once you really go to these fully differential circuits is that, typically, at least, back in the quote-unquote good old days when you were just dealing with single-ended kind of things, you could say that the gain of the amplifier was some number, right? Well, if you think about a fully differential amplifier, now you actually have two different inputs, right? You have actually the differential input that you're applying, but you can actually also have the common mode input that you're applying. And in fact, you have two different outputs as well. You actually have the differential output and also the common mode output. So now that you actually have multiple inputs and outputs, when you say what is the gain, you actually have to specify which input were you referring to and which output were you referring to. Okay, so in fact, in any real fully differential amplifier, you actually have at least 4 gains. Okay? By the way, for those of you guys who like to think of this sort of mathematically, this is really just saying that it's a linear system with 2 inputs and 2 outputs, so its gain is represented by a matrix, which is just 2 by 2, of course has 4 coefficients. Okay? Now, the gain we usually sort of like to think about is the so-called differential mode gain, right? That's the one that we're sort of traditionally are used to, right? Where we basically say, okay, if I have a differential input and a differential output, if I have like a perfect op-amp or OTA, I would want this gain to essentially be infinite, right? I'm also going to, of course, have a common mode gain, meaning from the input common mode to the output common mode. But the ones that are sort of, let's say, in some senses more interesting is that you can also get these so-called mode conversion gains, meaning that you apply a common mode input, but it actually causes a differential output. Or similarly, you apply a differential input, and it actually causes a common mode output. Okay, we'll say some more about those in a second, but those are usually related to things like mismatch or asymmetry inside of the circuits. And in fact, in some circuits, they're sort of inherent to the way that they actually operate. Okay? But so again, maybe just focusing on sort of this, let's say, matrix here, let's just sort of do a quick thought experiment as to what we actually want these gains to be. So as we already said, we want the differential mode gain to be infinite, right? That's sort of our standard signal in to signal out. That's usually, hopefully that's very clear why we want that. All right, so let's next ask ourselves what we want the common mode gain to be. Yeah, you want it to be 0. Now, why is that actually important? Why does it matter if the common mode gain is not 0? What could go wrong? Yeah?
Your output signal gets false positives.
You said the output signal gets false positives. What do you mean by that?
I mean that if the common mode gain is sufficiently high, then you won't be able to distinguish between what you want, which is the differential signal, and what you're getting, which might be interference or something.
Okay. So you said that if the common mode gain is sufficiently high, you may get into a condition where you can't actually tell between the differential signals and the common mode signals. You're basically right. I just want to maybe clarify it a little bit more. So what's like one particular situation where if you had a very high common mode gain, things can go really, really wrong? Or in fact, even just a reasonably, a not reasonably small common mode gain. Yeah? Voltage follower. Oh, okay. That's possible. That's not the example I was thinking of. But you were basically saying something like this. That is indeed possible. Now, we have to be a little bit careful because remember with followers, you're not really using it as a fully differential circuit anymore. Right? That's still actually kind of a single-ended output. But I'm actually thinking of even in a context where everything is all the way fully differential. You could, although even there, so it's true that may have, well, okay, actually, you kind of got to what I wanted. So let's say indeed you did something like this. Okay? That is indeed a possibility. Now, by the way, I'll mention one thing which is usually easier for people to sort of think about. Notice when you place the thing into feedback like this, that's kind of like saying you're taking just an infinitely long cascade of these amplifiers. Right? Because you take the output signal, you feed it back to the input goes back to another amplifier, and so on and so forth. Right? Okay, so indeed, actually, you guys took sort of one step beyond the answer I was looking for. I was actually expecting somebody to say, well, if I had a lot of these amplifiers in cascade, then now if I put some small little common mode error at the very beginning over there, at the end, it will accumulate and potentially rail the whole thing out. Right? You could indeed sort of argue that the follower is a similar condition. Okay, but really the point is you indeed want that common mode gain, ideally speaking to be 0, but in general to be small, simply because if it's not small, if you have a lot of these amplifiers cascaded together, small common mode errors initially could accumulate enough that you basically rail out the later stages, meaning you push them outside of the good common mode operating condition. Okay? All right, so let's ask the next question. What do we want this common mode to differential mode gain? So again, this is, I apply a common mode input, and I get a differential output because of it. What do you want that gain to be? Yeah, you want that to also be 0, right? And in fact, well, let me ask you guys. So now I'm going to give you a choice. You only get to make one out of two things 0. So you either get to make the common mode gain 0, or you get to make the common mode to differential mode gain 0. Who picks number 1 to be 0? Who picks number 2 to be 0? Okay, good. Indeed, number 2 is by far the most important one, right? In terms of it being really 0. Because the whole point was we wanted to do this thing, we wanted to do this fully differential amplifier, exactly to gain immunity from common mode noise, right? So in practice, by the way, what this really means is that when you build any kind of system, pretty much any junk that's unavoidable, you're going to put it in the common mode, if you can, right? So that means that typically the common mode is really, really noisy. It has all kinds of variations and movement and et cetera on it that are really not what you want from your signal. So because of that, that means that really, indeed, you better make sure you have very, very low common mode to differential mode conversion. Because if you don't have that very low, well, all of the junk you just intentionally put in the common mode will basically show up on your differential signal. Okay? So that is indeed very sort of important point to keep in mind. Now, okay, just one last question just to make sure sort of everyone, is on the same page. What do you want the differential to common mode conversion gain to be? So again, this is differential input signal, common mode output signal. Yeah, you also want this 0, right? Because, hey, why would I ever want to generate any common mode for my differential signal? Now, let's again maybe ask the question of, and now let's maybe do, well, okay, I won't be that mean. But as you can hopefully maybe tell, for that one, yeah, you want it to be 0, but that's probably one of the less important parameters. Okay, because if you sort of think about it, the only way this could come back and really cause a very big problem is if you had a reasonable differential common mode conversion, and in the next stage also a common mode to differential conversion, right? So in other words, this thing tends to get attenuated both by this being low, and if your common mode gain is low, that would also tend to attenuate that issue. Now, that's not to say you should just forget about this, right? Certainly that's not the case, but generally, out of, let's say, the priority on everything, that's not necessarily the highest priority to guarantee. Now, maybe the good and the bad news is that if you do a good job with this, meaning the common mode to differential conversion, typically you will also have a low differential to common mode conversion. Because typically the source of those problems is usually the same thing. So if you fix one, it'll usually fix the other as well. Okay? Does this make sense to everybody? Or? Okay, so one very common way that people like to sort of think about these different types of gains, and in particular to sort of characterize the behavior of their amplifier with respect to these gains, is rather than just sort of quote the gains directly, they like to quote these so-called rejection ratios. Okay? So what a rejection ratio typically means is it just tells you what's the ratio between the gain that you actually wanted, typically the differential mode gain, versus the gain to pretty much any other signal that might be in the system. Okay? So it might be from a common mode signal, it might be from, let's say in this case, the power supply, and so on and so forth. Okay? So I'll just give you sort of one note to keep in mind is that, you can define rejection ratios to just about anything you would like to. In fact, to some things that may not even be real terminals in your circuit. So for example, you could have something like, the temperature changed and you want to define a rejection ratio from temperature change to, how much your actual differential mode gain was. But generally speaking, indeed, the ones that you'll hear most commonly are the so-called CMRR, which is the common mode rejection ratio, and the PSRR, which is the so-called power supply rejection ratio. Okay? Now, there's a couple of notes I need to make here to make sure that things are really very clear. The first is, if you'll notice, the way I define this common mode rejection ratio here, I'm defining it as the ratio between the differential mode gain and the common mode to differential mode conversion. Okay? In many sort of textbooks or other contexts, they will actually talk about CMRR as being not what I've defined there, but instead the differential mode gain over the common mode gain. Okay? So just, again, user beware. I define this because, again, that's typically more what I care about. Right? You do care indeed about the common mode gain, but you care more about what's the common mode to differential conversion. Okay? So that's, again, why I've defined the common mode rejection ratio this way. Okay? The other point, which is perhaps actually not so subtle, but which is lost, in fact, in many even textbooks, is that you have to be really, really careful with how you use specifically the three parameters that I've defined here. Okay? Because as I'll show you in 1 second, you actually cannot independently define CMRR, the PSRR with respect to so-called VDD, and the PSRR with respect to so-called VSS. Okay? Now, to make sure that what I mean by that is clear, let me just sort of draw a very simple picture. Okay? So let's say we've got our fully differential amplifier here, right? Something like this. Okay, so the differential output, that's pretty clear. That's just going to be right there. Okay? Now this amplifier, of course, also has supply terminals, right? So if I was going to, for example, measure the common mode rejection ratio or anything related to the common mode, the way I would set up my experiment to do that would be to basically apply a voltage source as an example like this. Okay? So I would be moving those two inputs relative to ground, or relative to VSS. Right? Similarly, if I wanted to define a so-called power supply rejection ratio, the way I would do that, for example, would be something like this. Right? I would tie a voltage source basically between the VDD and the ground of the amplifier. Okay? Now, here's the real sort of very important point to keep in mind. Or maybe I'll even actually ask you guys. So, notice I've defined the voltage here. Let me call that or a potential here. That's potential number 1. Okay? Let me also define this as just being potential number 2. Right? 1 could be sort of what I called the common mode. 2 could be what I called the power supply. Okay? Well, how many other potentials can you define at the input of the amplifier? Or rather, in this circuit, what other potentials are left? Okay, you can do 2 minus 1, but so you actually shortcutted me. So what I was hoping someone would say would be that, well, okay, I could define another potential like this, which let's just call it 3, which would have been the common mode input relative to VDD, right? Now, as you just said, 3 is completely and 100% defined by 1 and 2, right? You cannot independently define 3 from the other two, okay? Now, the reason I mention this is that, again, you have to be really, really careful with how you use all of these sort of power supply rejection ratio kind of quantities. Because notice, if I really just have a VDD and a ground, right, there is no such thing as these 3 quantities being independently defined. Right? Because notice these 3 quantities are associated with potentials 1, 2, and 3. And if 3 is set by 1 and 2, you can't actually independently play with those 2. Okay? Or those 3, I should say. So again, be really, really careful with this, because this is sort of a very simple mistake to make that pops up actually quite often. All right? Now, the other sort of complication in this is that sometimes when people sort of sell you an op-amp, they have a positive supply rail, a negative supply rail, and a ground, right? In that case, again, user beware. You better make sure you understand when they said power supply rejection ratio, for example, for the positive rail versus the negative rail versus the common mode. Typically, that's defined with respect to the ground. But again, user beware, that may or may not be true. Okay? And in fact, usually for sort of the IC amplifiers that we're going to be dealing with, usually there is no negative rail versus ground. Usually there's just a ground and everything is with respect to that. Okay? Does this make sense to everybody? Or? By the way, anybody actually seen this before? Or? No. Okay. So hopefully this is clear. If not, by the way, you'll be getting sort of plenty more opportunities to actually play around with this, because in your project, I'll be giving you sort of a bunch of circuits to build, and I'll be mean and I'll actually put noise on the power supply and the common mode and things like that. So you'll have to be very careful to figure out exactly how that's affecting the rest of your circuit. Okay? So just as maybe one example to again make sure that all these points are clear, I just wanted to walk through sort of one, let's say, representative calculation of common mode rejection, or just an example of how sort of that comes into the picture. So to start things out, and again, just sort of motivate why we wanted a differential circuit in the first place, let's look at just a simple single-ended feedback OTA. Okay, so we're going to have our VI there, our CS, then we're going to have our OTA, again with a single-ended output. So we have our CF here. Okay, and this is, of course, going to be our V out right there. And as we had discussed, previously, let's say from whatever bizarre reason, you actually have some capacitance there to some error voltage. Okay, and let's call this capacitance CE. Okay? So first of all, what is our output voltage going to be as a function of both the input voltage and that error voltage VE? What is that going to be? Yeah?
So it'll be CS over CF times VI plus CE over CF times VE.
Yeah, exactly. I just added in some minus signs for you, but it's minus CS over CF times VI minus CE over CF times VE, right? What's that? No, the question was, will I add the minus sign for you in the midterm as well? No, sorry, it can't be quite that nice. So, given that this is the case, if you want to make sure that VE does not affect your amplifier, what do you do? Or what can you do? Okay, well, so the only thing you can do is get rid of CE, right? Or make CF large with respect to CE, right? Now, by the way, unfortunately, usually the CE has to do with, like, just as an example, you had some wire over here, in fact, maybe a lot of wires, because, for example, you made a really big capacitor for that CF. And oh, by the way, there's some other wire over there, and there's another wire over here. And in fact, there might even be some wire, if you're not careful, underneath your capacitor, right? So usually that has to do with just, there's stray parasitics in your layout. Now, indeed, you can do a lot of things to try and reduce that or make it as small as possible. But in general, it's really hard to make it go to absolutely zero, especially if you want a very compact layout with a lot of things nearby it. Okay? So the point here is really that it's actually pretty tough to make sure that, or rather, it's pretty tough to sort of, make sure that that CE is necessarily going to be as small as you want it to be. Okay? And in fact, even if you were to just sort of say, well, okay, I'll increase CF, that would mean you'd, of course, have to increase CS. Your area would get bigger. That would also then tend to mean that you're more likely to run into other wires that you actually need to run through that general space. Okay? So the point here really is there isn't much you can actually do to fix this problem. Occasionally, by the way, sometimes people say, well, okay, why don't I just make VE 0? Well, okay, that's nice. Sure, we'd love to do that, but that's not necessarily very easy to do either. Okay? So again, the real point here is that if we now start looking at a fully differential amplifier, and let's just go and draw that. So let's call that CS. Let's call this also CS. And you'll see why I left myself some space there in 1 second. And now I've got the fully differential connection. So I've got a CF here as well, and a CF here. Okay, and now let's say that I still have that coupling, right? So I still have a CE here and a CE there, connected to that VE. Okay? Oh, and I'm sorry, let me actually connect these. There we go. That's the terminal connection there. Okay, so if I do this, and everything is really as I've labeled, then if the OTA is actually good, meaning that it has a very low common mode to differential conversion, then now, basically, life is good. Right now, I could kind of make VE almost anything I wanted, and ideally speaking, it would have no effect on my differential output, right? That's exactly the sort of benefit of using a fully differential circuit like this. Now, having said that, what could go wrong that would cause this to not be so perfect? In other words, what could go wrong that would cause VE to again have an effect on the output? Yeah? Okay, great. So let's say, for example, that CS was not CS over here, but it was actually CS plus delta CS. And the other one remained just CS. Well, indeed, now you actually have an asymmetry in the circuit, right? So that if VE moves around, it would actually cause a differential input voltage into the OTA, right? That differential input voltage, of course, would then get amplified. As you then also said, well, if these two CEs are not exactly the same, again, I have an asymmetry, and that asymmetry would cause that VE to become a differential error voltage. Yes?
We're not positive, but it seems like if you're doing a layout, you're very likely to get the CEs not to be able to match anyways because your diffusion are going to be different widths.
So you said that it seems likely that if you sort of do the layout, that the CEs will not be the same.
What is dependent on your common mode voltage that VE is compared to say
Well, okay, so remember this CE, or these CEs, are really, in this particular context, I've drawn them as being capacitors, right? So that would mean that it's basically, there's some wire nearby that you're coupling to that has some other signal on it that I didn't really want to be coupled to. So let's actually draw maybe an example. So let's say that indeed you had your differential input lines like this, and let me just erase this so that it doesn't run into it. So let's say this is VI plus, and this is VI minus. Okay? So in fact, let me just erase the rest of that just to really make sure there's no confusion. And yeah, okay, I'll stick with the same color. So let's say that my layout looked like this. This is going to be some other signal. Let's just call this VSIG. Okay, and this is, let's say really this is my entire layout in the region that I'm interested in. So okay, so what's wrong with this particular layout from the standpoint of exactly the issue we were talking about? Meaning that if we wanted good common mode rejection. Yeah, it's not symmetric, right? In particular, I'm going to have probably a pretty big or a larger capacitor between that signal line and VI minus than I am going to have between that signal line and Vi plus, right? That would definitely cause an asymmetry. So now you guys tell me, what can I do to fix this? Yeah?
Well, you could have another VSig line to the left of VI plus.
Yeah, as an example, you could have another VSig over here to make the thing symmetric, right? That's one way of doing it. Now, maybe I don't want to do that because this signal I care about too, and I don't want to just have a bunch of extra capacitance there. What else can I do? Okay, I could indeed just add some shields in, and I'll draw this in a different color. Right? So as an example, I could maybe take a ground line there and a ground line here, right? And to put it around both of those signal lines so that at least most of the capacitance from the environment around it would go to the ground lines and not actually to these other wires. So by the way, it turns out if you're actually really paranoid, and sometimes you really do have to be that paranoid, you can even do things where you build a little Faraday cage around your signal. Okay, and so the way you do that is you take the lower metal layer, you just put a plate of metal that's again ground underneath the signal. Then you put a bunch of vias, you put something on the same metal layer that's ground, put a bunch of vias again, then on the layer above it you put ground, right? So you just build this little cage all around your signal, right? Now obviously when you do this, these sort of chip architects usually hate you because you've just taken like 3 metal layers for, one pair of signals, but hey, if you got to do it to make sure it works, sometimes that's what you have to do. Okay? Does this make sense to everybody? Or? By the way, there's actually one other clever layout trick that doesn't involve adding any grounds whatsoever. Okay. So there's actually 2 ideas here. So you said you're going to put it in the middle. That's true. That is possible. So that would mean that you'd basically have the VSig like this, and then your 2 lines around it, right? That is indeed one option. That really now relies on, because you've actually probably increased the coupling to VSig versus the previous example, so that really relies on you having good common mode rejection. But indeed, it'll make it much more symmetric. Okay. So you said that I could turn VI plus, and I'll just draw sticks now instead of everything. You said I could make VI plus and VI minus like this, and VSig like that. That is true, although in general, if VI plus and VI minus needed to go vertically, then I may not be able to just arbitrarily play this trick, but that is true. There's one other trick that you guys may have seen that actually, in fact, you have really seen, you just maybe never opened up the particular cables to look at it very carefully. There we go, twisted pair, right? So the other trick is basically you would take those 2 wires there, and I'll just draw it again with sort of sticks rather than the full wire, and you twist. Right? So if I do a twist like that, and indeed the VSig is running along the side right there, then if I do things ideally, then indeed I'll get perfectly symmetric coupling from each of those halves of the signal, each of those halves of the differential signal to that signal on the side. Now, by the way, specifically in the IC context, you have to really watch out if you try and do this, because this means you have to put like a via and a layer crossing, and you can never really do that exactly symmetrically. But nonetheless, people do occasionally play that kind of trick as well. Does this make sense to everybody? Or? Okay, great. So just as sort of one last, or a couple maybe last thoughts before we move on from this, given that we've now started talking about these sort of fully differential amplifiers and what we want to do in terms of making, what we want to make the gains look like, what I wanted to do is a little bit of a thought exercise about what would be sort of the properties of each of these 3 different types of input stages that I've drawn here? Okay? So in this first example, my input stage, this is often, by the way, called a pseudo-differential input stage, and I'll explain why in 1 second, where I don't have any tail current source. I'm just going to tie the 2 inputs, the sources of both the input devices to ground. Okay? This option over here, this option over here is actually sort of a more traditional option, let's say, where I'm going to have a real differential pair with a tail current source, but my bodies are going to be tied to ground. And then finally, I'm going to have this thing over here, which actually has not just the body's not tied to ground, but actually the body's tied to the source. Okay? So let's maybe just first start out, with asking you guys a simple question, and then we'll see sort of why the answers may be what they be. So if you are really, really paranoid about making sure that both your common mode and your common mode to differential mode gains are ideal, meaning small, which stage are you going to pick? Which one of these three do you think is the best one to use? So let's maybe start out. Who picks A? Nobody. Who picks B? Okay, good chunk. Who picks C? Oh, nobody. Okay, well, so there's a few people who didn't pick any that I, again, have to fail or something like that to get you to raise your hand. But it seems like most of the class indeed picked the right one. Okay, well, so let's maybe go through. Why did you not pick A? What's bad about A from the standpoint of everything that we talked about? Why is that not so desirable?
Just amplifying both sides, without you're not doing any projection at all, because you have the same common mode on both sides. It's just going to come out as odd.
Okay, so what you said is you're not doing any rejection of the common mode at all. And in many ways I agree with you, but let's be very specific to make sure everything is clear. Okay? So what you said, to be precise, which is indeed correct, is that if I look at the ratio of the differential mode gain to the common mode gain, that is indeed 1, right? Because you can't tell the difference between common mode and differential mode in terms of just a straight, the direct path of gain that we looked in that matrix before. That's absolutely correct. Now, here's the real question, though. What about the CMRR that I defined before? In other words, differential mode over common mode to differential mode gain. What's that going to be? There we go. So it depends on the matching, right? If everything was perfectly matched, that would still be an infinite number, right? The only problem is that if there is any mismatch whatsoever, that mismatch will show up directly as basically that differential mode to common mode to differential mode conversion, right? So in other words, as an example, if you had a little, well, let me draw it a different way. If this transistor was ever so slightly bigger than the transistor on the other side, so that it had a delta GM, right? Or equivalently, if the load resistance on the top, there was a delta R versus the other side, both of those would directly show up as basically the common mode to differential mode conversion. Okay? In other words, there's no attenuation of either of those effects, because as we said before, nominally the common mode gain is indeed just as large as the differential mode gain. So any mismatch directly is being multiplied by the same gain. Okay? That is indeed the problem with that particular stage. Not to mention that we did say, well, we wanted the common mode gain to be low. That we've clearly failed, right? But even beyond that, we're not really attenuating any of the mismatch whatsoever. Okay? So now, let's take a look at this guy. And let's again sort of be very specific. So for this guy, what's my differential mode to common mode gain? What's that ratio going to be? What's the common mode gain going to be? Yeah, it should be 0, right? Because notice, I've got a tail current source here, right? So if I apply a common mode input, which would just look, for example, like this, right? Then if that tail current source is ideal, that means that you can't change the current flowing through here, right? So in other words, this tail voltage, when you move the common mode around, would just ideally track the input such that the current through these two transistors is ideally the same. Okay? Does this make sense to everybody? Or? Now, by the way, if the ROs and everything are good, that would typically mean that this voltage here is basically just a threshold plus an overdrive below the common mode. Okay? Keep that in mind. We'll use that a little bit later on. But indeed, the whole point of adding this tail current source is that its output impedance is allowing us to reject the input common mode variations. Okay? And I won't walk through the derivation here, but actually this is something you can do sort of at home on your own. The output impedance of that tail current source basically shows up as a degeneration factor, meaning that you typically get the sort of common mode gain to be something like the differential mode gain divided by something like GM times the R of that tail current source.
Is this common mode gain being zero internet dependent on having like an RO, or is this?
Yes, so I am indeed assuming that the RO of this tail current source is infinite. If it's not infinite, then you won't get infinite column mode rejection. You'll just get something that's really set by essentially the GM of these devices relative to the RO of that tail.
What about the RO of the differential pairs? It seems like you could potentially have, like if you are trying to get slightly more current, you could potentially have rejection in your drain current.
Well, okay, so that's actually a very good question. So you asked, what would happen if I had a change in the RO of these transistors, or particularly the RO of the input devices was not infinite? Would that mean that I would actually have column mode gain? So now you guys tell me. If this tail current source down here is perfect, right, so if the tail current source is perfect, doesn't matter what these ROs are, because at the end of the day, the current is fixed, right? And if the current is fixed, and I dump that into just some resistive load at the output, column mode can't change, right? Does this make sense to everybody? Or? All right, so now let's ask the next interesting question. So here we said that at least ideally speaking, that differential mode to column mode gain should be infinite. Okay? But again, let's ask the sort of next interesting question. How about the differential mode to common, divided by the column mode to differential mode conversion? What's that going to be set by? This one's a little bit trickier, by the way. So let me ask you a specific question. If the GM of this device is a little bit different than the GM of that device, what's going to happen? Are you going to get some mode conversion or not? Okay, you will get a little bit of mode conversion, but the question is how much? Any thoughts? Yeah?
Maybe the difference of the GMs times the RO of either one, assuming that it's the same.
Okay, so you said the difference of the GMs times the RO of either one. Turns out that's what I would have actually gotten even over here. Okay? So you have to remember one thing. This tail current source over here, right, that's still forcing the net current that's flowing to be the same. Okay? That means that when I apply that column mode voltage over here, any sort of change in current has to flow completely through that upper loop, right? That actually means that the larger, or rather to say it another way, the larger this output impedance is, the more you'll actually still reject that error. Okay? It's not to say that you'll, for any finite output impedance, of course, you will still get some finite conversion, but it's being attenuated, right? Because you can kind of think of this as just being, like we said over here, because the column mode gain was high to begin with, when we put some small asymmetry in, we just basically directly multiplied by that column mode gain. Whereas here, if the column mode gain is low to begin with, then even if we put a small asymmetry in, we're still attenuating by that small column mode gain. We're still multiplying by that small column mode gain. Now, having said that, there's still one more effect we have to be very, very careful about, which unfortunately this particular structure is not perfect at dealing with. Well, we talked about mismatch, but there's another form of mismatch that we haven't talked about yet. And here's where, again, you have to start really thinking very carefully about these transistors. And in particular, look at the difference between B and C. Threshold. It's related to the threshold, but what else? There we go, GMB. Right? So remember, if you move the body to source potential around, there's another transconductance, which, by the way, is basically that bipolar transconductance. Right? There's another transconductance that actually will cause changes in the current. Okay? So notice, because this is ground, right, remember we said before that this source node here, if you move the column mode at the input, ideally this source will actually track with it. Well, even if I have a perfect current source, because this side is ground, that common mode voltage directly shows up on the GMB, right? Because if you move this common mode relative to ground, that source ideally moves exactly the same way, and therefore the body voltage or the body to source voltage is being exactly modulated by the common mode. Okay? That means that now if you have any mismatch on the GMBs, directly shows up at the output. Okay? No attenuation from the current source, no matter how good the current source is. Okay? Does this make sense to everybody? Or? Yes?
Slightly confusing still about why having the current source there is kind of attenuated mismatch from just the GMs, but we do that with the GMBs.
Okay, so here's the trick. Remember, the whole idea here is that in this case, the reason why the common mode rejection was bad was because basically if you moved the common mode around, you directly changed the VGS of these transistors, right? That means that any mismatch in the GM is directly multiplied by the common mode voltage, right? Here, if I move the common mode voltage around, if this tail current source is perfect, ideally speaking, the VGS doesn't really actually change. If the VGS doesn't change, even if the transistors aren't perfect, guess what? They still don't actually create a large error at the output. Okay, that's really the key. Which again, that's also why there's a contrast to this body voltage. Right? Because in this case, if you move the common mode around, even if the tail is perfect and it moves, sorry, body to source voltage changed. Okay? That's really the trick. Is that more clear to everybody? Or? Okay, now hopefully, we've maybe beaten this a little bit to death, but hopefully that's now clear why this particular option is actually the best one. Okay, at least from a DC common mode rejection standpoint. Because now in this particular case, since we've tied the body to the source, now we don't have the same issue anymore, right? If this tail node actually moves, the body actually moves with it. There's no change in the body to source voltage. You again get to reject any mismatch in those transistors. Okay? Does this make sense to everybody? Or? Now, by the way, what we've mostly talked about so far is basically common mode rejection at DC. So what unfortunately happens at higher frequencies that tends to make your common mode rejection get worse? Or rather, what parasitic is typically there? Yeah. Yeah, exactly. There's always some capacitance on this node here, right? And unfortunately, as you go to higher and higher frequency, the impedance of that capacitor goes down, right? At some point, if that capacitor becomes too low of an impedance, then really there isn't any difference between these two, right? Because for all intents and purposes, that source node just becomes ground, right? Which means that, again, you apply a common mode input voltage, directly changes the VGS of the transistors, okay? So by the way, that actually does mean that, in fact, if you looked at the difference between B and C, depending upon exactly how you've set things up, B could actually be worse than C at high frequencies. Simply because when you do this, you now pick up whatever capacitance there is from the well to the rest of the substrate around it. If that capacitance is larger than the capacitance you had here, that could actually be a bad thing to do, okay, at least at that particular frequency. Does that make sense to everybody? Or? Okay, great. So last thing that I just want to sort of... Oh, I'm sorry. Actually, one more quick thing that we'll do here. So again, just to make sure this is sort of all really 100% clear, what I want to do is just go through an example of sort of how power supply rejection ratio, or really how the power supply might actually sort of couple into your differential output, or rather how much it would sort of change things. So let's just draw this sort of very simple, fully differential OTA, okay? And again, what I'm going to do is sort of excite this thing with some power supply noise, okay? So I'm going to do that again by applying a voltage source between the VDD and the ground, okay? So what I want to ask you guys is, if I move this VDD over here, let's say by plus 1 millivolt, what's going to happen to the common mode at the output of this structure? Ah, there we go. Okay, so the answer you said, which sometimes people skip this one, is, well, it really depends on how you bias those PMOS devices. Okay? So what are my two options in terms of biasing those PMOS devices? What two ways could I do that? Conceptually, at least. And I don't mean like with current sources or anything like that. I really mean, I've given you a voltage source. I'm going to let that voltage source define the bias. But, what are my two options in terms of connecting that voltage source? There we go. Okay, so option number one, which I'll do in red, is I could connect that voltage source like this, right? Option number two, which I'll do in a different color, let's use black, is to do that. Okay, so that's 2, and the other one is 1. Okay? So by the way, typically if you've done things right, which way should you be doing the bias? Should you be using 1, or should you be using 2? Okay, I got one answer sort of, on the side. Who thinks it should be number 1? Oh, there's 2 of you guys. Who thinks it should be number 2? Wow, there's still a bunch of people I have to fail somehow. Okay, so for the guys who said number 1, why did you say number 1? Okay, well, you had to guess. Good. So for the guys who said number 2, why did you say number 2? Okay, you said that PMOS is a lot of times you're referencing to VDD. That's actually absolutely correct, but what do you really mean by that? And I'll give you a little bit of a hint or a reminder in our previous discussion. We said in the previous discussion that generally we didn't want the VGS to change if we didn't want things to get messed up. It's true the bulk is indeed tied to typically to the source, meaning to VDD in this case. But again, why is it that 2 is different than 1 in terms of not making the VGS change? Yeah, exactly. If I do it as 2, I'm forcing VGS to be whatever I wanted it to be, right? So this is really, by the way, the key almost always to making sure that your design doesn't have like stupid errors in terms of power supply rejection ratio. Because 90% of the designs that I've seen that had really, really big power supply problems, there was just a really dumb error like this. Where the dumb error was that there was a signal, or really there was an input that was referenced to a particular voltage, or to either to VDD or to ground. And unfortunately, the biasing was done in a way that the referencing on the input was exactly flipped. Okay? Because notice in this context, if you did biasing number 1, how much would the common mode voltage change due to VDD moving, for example, by 1 millivolt? And I don't need a number like, analytically or conceptually. Yeah, it would change by 1 millivolt times the GMRO of that structure, right? Bad news. Okay? Whereas if you do it as number 2, then you really just have sort of an RO, you have some resistive divider in there, which typically way, way better. Okay? So again, keep this in mind because 90x% of the problems I've seen all boil down to basically understanding this one particular concept. Okay? All right, so unless there's sort of other questions on that, let me just mention again one last sort of important thing that tends to come up when you're dealing with these fully differential amplifiers. Okay? So let's say I've got some fully differential OTA. Okay? And you want to go and do some simulations on it to characterize it. Okay? And let's say that it's actually in some capacitive feedback like I'm drawing like this. Okay? Well, I don't know about you guys, but I'm lazy. Right? So I don't typically like to specify like a bunch of different voltage sources for differential versus common mode and all these other things. And in fact, I even like to measure just whether the differential voltage is or what's the common mode voltage. So very common sort of, let's say, trick that you would play. You say, well, you know what? I'm going to build some box that takes, for example, a differential voltage and a common mode voltage and converts it to the actual terminal voltages that show up on my structure over there. Okay? And similarly, I could basically take the same box, but just turned in reverse, and have it give me the differential output and the common mode output. Okay? So, when you first do this, typically the way you would build that box is the following. You'd basically say something like, well, okay, I can take my VI plus, I can take my VI minus. I'm just going to sort of define those two as terminals. And then what I'm going to do is define a controlled voltage source, typically with respect to ground, that would be VI plus minus VI minus. And in fact, actually, let me not make that relative to ground. Let me make that relative to the input common mode. And this would be like my differential output, right? That's how I would do, for example, the box that's sitting over here. And in fact, I might even try doing it as the box like this. Okay? Oh, I'm sorry. No, there we go. This is actually to ground. There we go. Okay, so that would be, for example, how I would get my differential voltage at the output. And you could do something very similar for the common mode. Okay? It's a VI plus minus VI minus. Okay? It's just taking the difference of those two voltages, which is literally what the differential voltage is. Right? Is that clear or no? So this particular example would be basically this box right here. Okay? That would be, well, it would be actually half of that box because I haven't shown you how to do the common mode, but it's the exact same idea. Okay? All right, so now you guys tell me, what's wrong with using the box that way or building a box that way? Yeah, exactly. I've totally messed up the loading, right? Because I've now completely isolated these outputs from the actual final output, right? So for example, if there was some capacitive or any other load over there, it would just be lost, right? Because I have an ideal voltage source here. Sorry, you can't see it, right? So maybe in this particular context, doing it at this box, if I really didn't have another output, that wouldn't be so bad. But clearly, if I try to do something similar on the input side, again, bad news, right? So it turns out the way you'll typically want to build that box, at least again in like SPICE or Spectre or whatever it is basically with so-called balins. Okay, so the idea is the following. I could take, for example, my input differential voltage, connect it to two transformers, where the turns ratios on the transformers will be 2 to 1. Okay? And then on the other side, these will be the one side. Okay? There I would connect this to the input common mode. Oh no, I'm sorry. This would be connected to the input common mode. That's Vout minus. That's Vout plus. Okay? And it could actually, in this particular case, because I've done it with transformers, actually doesn't matter what's an input and what's an output. Okay? Because basically, because I use the transformer, then anything that happens on one side will actually affect the other side as well. Okay? Now, just to make sure this is clear, the reason there's a 2 to 1 ratio here is that if you think about it, if I apply an input differential voltage, what that means is that I want to apply half of that differential voltage to the plus side and half of that differential voltage to the minus side. Okay? So that's why there's these sort of 2 to 1 turns ratio here, just to make it so there's half on each side. Okay? And notice by sort of stacking these two transformers like this, I've just added the two voltages together at the output in order to generate the differential voltage. Okay? Does this make sense to everybody? Or? By the way, main reason I mention this is just that, again, it's very common to sort of do these fully differential structures that you're going to want to test and characterize in SPICE. And again, I'm just lazy. I really don't like writing a lot of different voltage sources. So if you build this little box, you can basically put that box in all of your differential circuits. And then it gives you a very convenient point to just measure, okay, what was the input differential to output differential? If I move the common mode around, what happens to the common mode? And so on and so forth. And again, by doing this, by making these transformers ideal, it has no impact on any of the loading or anything else in the circuit. Does this make sense to everybody? Or? Okay. So unfortunately, on-chip, well, okay, it depends on the application. For most of the stuff we're going to talk about, no. Simply because making balins actually work from DC to any other reasonable frequency generally is not possible. Okay, because remember, these are based on sort of magnetic coupling. And at DC, there is, you can't really actually measure anything. There's no signal that gets transduced to the other side. Okay? Is that clear? Or? Okay, yeah. So now, if you were doing something that, is around a certain carrier frequency, then you can do these things quite often. Now, the question then just becomes, how big is the balun? How much loss does it incur? And so on and so forth. But in SPICE, I can put perfect transformers in, no problem. All right? Okay, any other questions on this? Or? All right, great. So if not, let's go ahead and actually move on to the next set of lecture notes that I handed out last time, which is now basically talking about what will turn out to be our sort of workhorse OTA. Okay? So hopefully you guys have heard of folded cascode before. If not, we'll sort of cover that a little bit today. But just sort of by way of motivation to explain why it is that this folded cascode will become our workhorse OTA, we need to look a little bit at sort of one of the key limitations of our simple differential input OTA. Okay? So here notice I've basically used, a good input stage, meaning I actually had a real tail current source here, and hopefully I've made this bias voltage for these sort of PMOS tail current sources. I've done that appropriately as well. But what I want to do here is actually look at, given this particular structure, what's the largest swing I can actually get at the output? Okay? And in particular, as we'll see in 1 second, unfortunately the swing you can get at the output of the structure is actually very closely tied to the input column mode voltage. Okay? So to see why that is, let me sort of define just a couple of things. Let's say that this device here has some minimum voltage swing or rather some minimum VDS that it can tolerate. Okay? And any VDS, any VDS larger than that, and it'll sort of come out of SAT, you won't get enough swing. Okay? Similarly, let's assume that that input device there also has some minimum VDS, and that it has some known or given V star. Okay? So what I want to ask you guys is, if I look at sort of one of these outputs right here, what's the sort of maximum output voltage that you can support while still keeping everything in saturation? And by maximum, I'm measuring everything relative to ground, by the way. So what's the max potential? And maybe I'll just define it to be clear. That's V out right there. What's the maximum V out you can get and still keep things in saturation? Yeah, exactly. It's just VDD minus V min P, right? Okay, now similarly, what's the minimum voltage you could get there? Well, okay, now we have to be a little bit careful. I'm going to define this as VXX, okay? And we'll fix what VXX is in 1 second. But if I told you what VXX was, what would be the minimum output swing or minimum output voltage you could get? Yeah, exactly. It's just VXX plus V min N. All right, well, so now, what is VXX? What is that tail voltage? And by the way, this is where I said you should keep something in mind from earlier. Okay, you sort of did it, but I think it was a little bit flipped. So I just needed to find one more thing to make sure that's sort of absolutely clear. If I told you that this is VCM in relative to ground, now what is VXX? There we go. It's VCM in minus the threshold minus the overdrive. And here's where I'm going to wave my hands a little bit. I'm going to pretend that the overdrive is the same as the V star. Again, they're really not, but just pretend that they are. Okay? Okay, well, so notice if I'm now interested in what's the output swing you can actually get, right? All I have to do is, of course, say V out max minus V out min. Okay? And if you just sort of plug all those things in, I'm not going to sort of write out the whole thing. What should hopefully be clear is what you get is VDD minus VCM in minus a whole bunch of other terms. Okay? With those other terms, involving V-mins and thresholds and things like this. Okay? So I claim this is actually very bad news. Okay? And again, really this sort of result is the thing to notice here. Okay, that's really bad news because basically what that means is that you have a direct coupling between the swing you can get and your input column mode voltage, right? So the wider the input column mode voltage range you want to support, in particular the higher the input column mode voltage, the less swing you can actually support at the output, okay? And again, if you think about a sort of general purpose OTA, that's bad because, the wider the input column mode range you can support, the more sort of places you can actually use this kind of design, okay? And in particular, just to make it sort of clear, if you really work this out, for modern technology, by the time you're done, even with, let's say, a 1 or 1.2 volt supply, you're typically left with only a couple hundred millivolts of swing after you've sort of taken care of a reasonable input column mode range, okay? So again, that's actually really the sort of biggest disadvantage of this particular structure, is that the column mode range and the swing are intimately tied to each other. You can't sort of increase one without decreasing the other, okay? Does this make sense to everybody, or? Okay, so because of that, that's actually why this so-called folded cascode tends to be the sort of workhorse OTA that people will use. Now, before I go too much further, how many of you guys have seen a folded cascode before? Almost everybody. Okay, so that's good. The whole trick with a folded cascode, just for the few who maybe have not seen it before, is very simple. Conceptually, it's actually doing the exact same thing as a normal cascode is. The only difference is that rather than putting sort of another device in series like this, I'm actually just going to take the current from my input pair and feed it to another cascode that's sort of turned on its side, okay, or folded is kind of where obviously the name came from. So the point, of course, is that if I look into here, I still have at least nominally you would think sort of a 1 over GM impedance. We'll come back to that particular point a little bit later. But basically, I'm still looking into a sort of cascode device, right? Or into the source of a cascode device. It's just that now, rather than sort of stacking everything on top of each other, I'm making it so that whatever voltage drop I needed across here could also be supported across that cascode device. In other words, I don't have to sort of pay for it twice going from VDD all the way to ground. Okay? So, the reason that this is now very good in terms of the issue we talked about before is that notice, as I move this column mode voltage around, that affects Vx, or Vxx, but really, to zero order, it doesn't have any effect on the node over here, right? Because these two nodes are really largely pinned by that bias voltage, right? That means that the swing I can actually get at the output is now actually decoupled from the input column mode range. Because as long as I can make these two nodes here sit in a reasonably good point relative to that common mode, right, then the whole structure should still actually work, okay? So again, that's really the biggest advantage of doing this folded cascode kind of design, is that now I really can sort of make this input column mode range relatively wide, but still support a wide output swing at the output. Or really, to say that more accurately, those two parameters are really decoupled from each other to a very large extent. Okay? Now, this whole thing may look kind of complicated, but it turns out that for some very sort of, let's say, simple reasoning, it's actually pretty straightforward to design these guys, or rather, I should say, it's almost the same to design these folded cascode OTAs as it is to design the much simpler structure. Because it turns out there's actually not that many degrees of freedom that you have. Okay? And to understand why that is, I'm going to ask you guys a question. So, clearly if this is ISS over here, then each of the input devices, at least nominally speaking, meaning with zero differential input, will be carrying ISS over 2. Okay? So now I want to ask you, if I took this device over here as an example, if I want to build this folded cascode and really make sure it works over a wide range of sort of input conditions, what do I need to make that bias current right there? Same. When you say the same, what do you mean? ISS over 2. Okay, so let's try that out. Let's say I made this ISS over 2. If I had ISS over 2 flowing through here, how much current is flowing through this upper branch? None, right? Because I have ISS over 2 here. Well, okay, let me be careful. ISS over 2 here, ISS over 2 there. Zero current can be flowing in the top, right? So that can't happen, right? That's no good. Well, I mean, or maybe it's okay. Well, I guess in principle, maybe it would have been okay, except that obviously the whole upper branch would be doing nothing, and then, life is not so good, right? Okay, so can't be ISS over 2. So clearly it's going to have to be larger than that. Now I claim actually that, we can even specify exactly how large it has to be. And again, the key to keep in mind is I want this thing to basically always work nicely, no matter what input differential signal I apply. So just maybe as a hint, what's a kind of extreme differential input signal that I could apply? Okay, yeah, as an example, I could sort of do something almost as bad as tie this to ground and tie this to VDD. In that particular condition, what would happen? What would happen to the currents flowing through these two transistors? There we go. So that's the key. If I did that, all of the current from the tail would be flowing through that one branch, right? Which would now make this ISS. All right, so now you guys tell me, what does the current through this device therefore have to be if you want to make sure you can support that? Yeah, it has to be ISS, right? Because again, if you want to make sure that the amplifier basically doesn't clip or doesn't sort of get really messed up due to you applying this very big input voltage, then you indeed have to make sure that this device over here can handle the full current coming from the input. Okay? Now, that's not to say that the amplifier won't become nonlinear in this condition. It'll just become nonlinear due to the input devices. And there's nothing you could have done about that anyways. In other words, you don't want it to become nonlinear because of the output devices. Okay? So, by the way, if that's the case, what does that mean that this current, at least, on a nominal bias condition, and let me actually do that in blue just to make sure that, everything's sort of consistent. So, by the way, blue here is going to be sort of the nominal bias current, right? So we said this has to be ISS. What is this nominal bias current going to have to be? There we go, ISS over 2. Right? Because notice, nominally speaking, you've got ISS over 2 flowing from here. And if you've got ISS there, there's another ISS over 2 flowing through the top. Okay? And indeed, this is very typically exactly how you have to build these circuits. Okay? Does this make sense to everybody? All right, so now, given that this is the case, turns out we can now actually also very quickly figure out what the noise factor or the excess noise penalty is going to be from this amplifier relative to just sort of a ideal common source amplifier. Okay? So just to make, maybe just as a reminder, just to make sure everyone's sort of on the same page on that, if I call this M2, I call this M1, this is, let's say, some bias, that's the input, and that's the output. What is the noise factor for that amplifier? And again, just as a reminder, that noise factor is in noise density. What's the ratio of the total noise current at the output of this amplifier relative to the noise current due just to the input device? So what did we say that noise factor was? Anybody remember? Yeah, exactly. It's just 1 plus V1 star over V2 star. Right? Because remember, the currents are the same. And therefore, the only thing that sets the ratio of the GMs is the ratio of the V stars. Okay? So now, given that that's the case, and given that we just said a second ago, we're going to have ISS. Oh, I'm sorry, I should have done it on the other side. We're going to have ISS over 2 flowing through M1. We're going to have ISS flowing through M3. And we're going to have ISS over 2 flowing through M5. What now would be the noise factor of this folded cascode amplifier? By the way, there's at least one term in the expression that, you shouldn't even have to think about. Okay, there we go. 1 plus. All right. We're getting somewhere. Turns out there's only 2 more expressions we need. So what are those? Oh, VBN2 and VBN1. Careful with VBNs versus VStars.
Or so, okay, V star and 2 V star.
Okay, there we go. So you said that there's a VStar, and I'm sorry, unfortunately there's only an M3 and an M5 here, so let's just make sure we're very careful with that. So what are the ratios of the VStars, and what are the factors we have to apply to them? There we go. Okay, you said 2. So just give me the expression, and we'll make sure we understand where it came from. Oh, oops. Yes, that's right. Okay, so let me just write that out, and then we'll make sure everyone understands why. So this is going to be 2 times V1 star over V3 star. Okay? And just to be totally clear, the reason there's that factor of 2 is because M3 has double the current of M1, right? So if it's got double the current, you have to double whatever the sort of V-star ratio was, right? Make sense to everybody? Or? All right, so we've only got one more term left. What's the last term? What else is going to contribute noise? Yeah, okay, that guy up over there. So what's that ratio going to be? Somebody other than DJ? Yeah, exactly. It's just V1 star over V5 star. Right? That's it. Okay? And again, the reason that here there's only a factor of 1 is because there's the same drain current through M5 as there is through M1. Okay? So indeed, this is the noise factor of this folded cascode OTA. Now, notice this is clearly worse than that sort of simple, normal. By the way, this kind of design is usually called a telescopic OTA. This is indeed worse. Okay? So that's the penalty that you pay for decoupling the input column mode versus the output swing. Because obviously, in general, you'd only do this in the condition that it really allows you to get a lot more swing than what this noise factor penalty would sort of take away from an SNR standpoint. And in general, that is indeed actually the case. Does that make sense to everybody? Or? Okay, so if that's clear, what I want to do now is just sort of run through kind of a quote-unquote characterization, a lot like we did last time for sort of characterizing that simpler OTA, just to point out a few additional issues that you really should be keeping in mind, both with respect to the folded cascode OTA itself and just more generally with differential amplifiers, okay, or differential OTAs, I should say. Okay? So this is just sort of showing you the schematic of the particular OTA that I'm going to be playing with. By the way, I should mention, I happen to choose a PMOS input pair here, exactly because I wanted to allow myself the capability to tie the body to the source. Because in general, in most CMOS processes, this is something you can do. You actually have an independent N-well, but you may or may not have the ability to tie the body of the NMOS devices. For that, you need a so-called triple well process. Okay, so here I just chose the PMOS device because indeed that's what I needed in order to allow myself to do this. Okay? Okay, so this is sort of the schematic. I'll, by the way, mention that all of the simulations I'm going to show you are not from our technology. They're from some other technology. So, don't try and take these and, run with this design and use it in the rest of the semester. It won't help you. But the point, of course, is that, we'll be looking at some issues that will be relevant regardless of the technology we're talking about. Okay? So first, a lot like we did last time, let's just take a look at the sort of biasing of this particular amplifier. Okay? So there's a bunch of different curves here. I'm not going to sort of spend a ton of time on, which curve is which. That's actually not super critical. The only thing that I did want to point out is that it is actually quite useful to do one thing. So if you'll notice here, I actually sort of, it's maybe not the most obvious, but I put a little bit of a break between sort of how much current was coming from the top leg of the amplifier versus how much current was coming from the bottom leg of the amplifier. Of course, at the end of the day, these two are really just shorted together. But I wanted to break this thing apart because what I want to do is I want to check that actually I'm really going to get the currents that I expected to or that I intended to, even across a very wide range of input voltages. Okay? So in particular, if you sort of focus on the plots here, and let me just make sure I've got the sort of labeling correct. Right? As an example, what I want to make sure is that when I apply a really big sort of differential input voltage, I want to make sure that, for example, I'm getting all of the current actually being handled in M3 and M4. Right? And so that's as an example, by looking at this M3 curve over here, you can see indeed it's actually able to support however much current it needs to actually, even across this entire input differential voltage range. Okay? So just as an example, if you sort of didn't bias things correctly, or you didn't actually have sort of let's say, enough default current in that device to begin with, what you might see is that all of a sudden the current actually drops as you skew the thing too heavily one way or the other. That would tend to indicate that something sort of fell out of saturation, went into triode, or the voltage across it dropped very heavily. Again, that would indicate that something is basically clipping that you didn't intend to. Okay? So again, the point of these plots is really to just sort of debug that you've set the amplifier up the way you intended to in the first place. Okay? And in particular, indeed, pay attention to sort of the individual branch currents to make sure that they really are, basically, as in this particular example, that you're actually able to handle the full current across the entire input voltage range. Okay? So similarly to as we had done previously, the next step, of course, is just to plot the low frequency gain. And in this case, I'm plotting the differential mode gain only. There's obviously other gains as well, but for here, let's focus on the differential mode gain. And by the way, I should also mention I've plotted both the large signal gain and the small signal gain. So as we talked about last time, it should hopefully be clear, this blue curve is the large signal gain. Okay? So as again we've sort of talked about several times now, this plot you'd use in several different ways, right? As an example, you could say something like, well, if I want to make sure that I have a gain of at least 100, that would tell me that I can have this much swing at my output. Okay? So as an example, in that particular case, it would say that I could do something like about, I don't know, maybe close to 4 volts of differential swing at the output. Maybe it's more like 3.8, 3.7, something like that. Okay? Now, I do want to point out one particular thing here, which is, if you'll notice, I just said that my differential swing was something like about, 3.8 volts. This particular technology actually has a power supply of only 3.3 volts. So, I just stated a second ago that I'm getting swing larger than my power supply. So did I break, am I doing something wrong? Did I break some physics somewhere, or is this actually okay? What do you guys think? That is really good. That is correct. But the question is this just, a bogus spice kind of thing, or is this real?
Are you kind of measuring the maximum positive swing you get with a very low current mode voltage versus the same thing with the opposite thing with a very high current mode voltage?
Okay. So if I could rephrase your question, I think your question was, did I cheat in some way? And the short answer is no, I did not cheat. So I will say that indeed this is real. Okay, now you just have to think a little bit carefully about how in the world I'm getting more output voltage swing than my power supply. Nope, I'm not cheating. Yeah?
Is your OTA subject to a different supply than your PMOS pair?
Oh, okay, so you asked if my OTA is subject to a different supply than my PMOS pair, and again, the answer is no, I'm not cheating. So now you have to think a little bit carefully. So this is a fully differential amplifier, okay? And I'm plotting the differential swing. So let's just do a very simple thought experiment. And I'm going to do something actually kind of bad, but it'll make the point. So let's say I built my amplifier just out of an inverter. Okay? If I put a high enough input voltage, for example, onto this side, let's just say I put in a VDD over here, you'd get 0 at the output, right? And if I put 0 over here, you would get VDD at the output. Okay? So what would my differential voltage be in that case? And let's make this the plus side and that the minus side. What would my differential voltage be? Yeah, it's minus VDD. Okay, let's do this in another color. If I flip these two, so I make this 0 and this VDD, which of course means that this will be VDD and this will be 0, What's my differential voltage? VDD. What's my swing? 2 VDD. Okay, so indeed I didn't cheat. The only trick I'm playing is that because I'm measuring the voltage or the output as the difference between two voltages, indeed I can actually go beyond the power supply, right? Because in the limit, I could actually get all the way up to 2 VDD of swing. Okay? We'll talk actually a lot more about this later on down the road, but this is actually one of the sort of very common benefits people quote about differential circuits, is that you can actually get double the swing of what you could often get otherwise in the single-ended context, simply because you're taking the output as the difference between two on-chip voltages. And each one of those on-chip things relative to the other can have a difference of VDD, okay, in either direction. Does that make sense to people? Or? So again, no cheating here. This is correct. Indeed, you could get all the way up to, ideally speaking, twice of the supply voltage for your differential swing. That's not to say you really will get double. Notice, right, I only got something like 3.8 volts when my supply was 3.3. But nonetheless, the fact that it's larger, as long as it's less than a factor of 2 larger, physically is actually possible.